Right. Good morning, everyone, and welcome to the fourth in the series of webinars from the Industrial Transformation Research Hub in Biocatalysis for Pharma. My name is Elizabeth Gillam, for those who haven't met me before, and I've got the pleasure of coordinating and introducing these webinars. Before we start, I just wanted to mention a little bit about the Research Hub and these webinars. At the moment, the Hub is a group of academic researchers with complementary expertise, which we plan to apply to problems associated with the use of enzymes as biocatalysts in pharma. We hope to engage partners from industry to help us leverage governmental and other funding to support our research on projects relevant to and designed with pharma. The emphasis in these webinars is going to be on presenting some of the science that's led to the formation of this Research Hub. And through the webinars, we aim to introduce you to some of the members of the Hub and to demonstrate the expertise that they bring, as well as to illustrate some of the projects we could pursue in the Hub. We hope that these webinars will become a forum for discussion of the priorities we need to address in order that enzymes can be used to their full potential in chemical processes. But these webinars will also serve as a bit of a model of what to expect from the regular forums that we will use to communicate outcomes from the Hub to ensure participants have timely access to information and tools resulting from the research underway. We have a number of seminars coming up in the next few weeks, and the schedule is shown on the next slide. We're almost halfway through the series now, but if you've missed any webinars to date, we do have a YouTube channel to which all the webinar recordings have been uploaded. So today our speaker is Professor John Woodley from the Technical University of Denmark. John is a bioprocess engineer who specialised in the biological synthesis of useful chemicals using biocatalysis and fermentation. To date, over the last 30-odd years, John has worked on various cytochromes P450 and other enzymes relevant to pharma, including alcohol oxidases, carbohydrate oxidases, biovillager monooxygenases, and transaminases. So without further ado, I'll leave it up to John to tell us about how he applies his expertise to addressing the issues related to scaling up P450 and UPO reactions, a key priority that we want to address in the Hub. Thanks, John.
Thank you very much, Liz, and good morning, everybody. My pleasure to tell you a little bit about some of the scale-up work we've been doing at DTU, Technical University of Denmark. We have this hub where we are interested in really working with biocatalysis for pharma, but I have to say that I think a lot of what I say is applicable not only to the pharmaceutical industry, but to other industry sectors as well. Just a little bit of background to say that over my career, I worked on many different types of enzyme and the scale-up of these enzymes, but in particular, I think I've long time had a focus on biocatalytic oxidation, which I think is a particularly fascinating type of enzyme catalyzed reaction. So over the years, I've worked on dioxygenases, biovillager monooxygenases, P450s, as mentioned, oxidases, and then more recently on unspecific peroxygenases as well. And obviously, the first four of these all require molecular oxygen. And the last one, we supply the oxygen via hydrogen peroxide. In many of these cases, this is also a real challenge. And we'll come to this a little bit later about the supply of oxygen or supply of hydrogen peroxide and how to really deal with this. So while my focus is on process design, scale up, scale down, it also, in particular, in the context of what we talk about today, is involved also with oxygen supply and how to supply oxygen in the right way to these types of reactions. So some reactions are clearly easier to scale up than others. We know already in the pharmaceutical world, there are many enzyme catalyzed reactions, and it's fantastic to see the developments which have taken place in the last 10 to 20 years. When we think about scaling up of new types of reactions, of course, those enzymes maybe for newer types of enzyme may be identified in a much earlier stage in the pharmaceutical pipeline. But at some point, we come to the stage, well, now we really need to scale this up. So, of course, it's not in this very early stage. Maybe we identify some interesting enzymes, but then later on, we say, okay, now we really want to scale these as well. And part of the argument here for using enzymes is, of course, the selectivity, the fact we can reduce the number of steps. But as I also mentioned in some of these papers here, the importance of a sustainable production as well is also a very important part to this. So let me give you a little bit of background to the whole issue of scaling and a little bit how I see that. So the first thing to say is that when I'm talking to companies, something that becomes very clear to me is that the time which it takes to develop a new process, to come all the way from the discovery in the lab to industry, really is too long. And especially in the pharmaceutical industry, of course, that's a particular concern. Speed is everything here. So we really want to be a little bit more like the hare and a little bit less like the snail. That's really the concept here. But I think it's also right to say that the development of these types of processes is also difficult. We inevitably have to use protein engineering here. We need the tools of protein engineering to improve the process. And this requires quite some interdisciplinary work also with the process engineering parts of this as well. So my philosophy for some time has been to try to divide the process development into two parts. One part is to say, how do we get sufficient economic metrics, sufficient intensity in the process? So we move from what we have in the lab at first and now to try to intensify this process. And then in a second stage, we then try to think, okay, how do we increase the volume of this process? So that's the conventional way of really describing scale up. And I think that dividing these two is important, because if we try to shortcut across here, we of course may end up with a process which really does not fulfill the metrics which we need. We know from an economic perspective, or indeed also sustainability perspective, these are the metrics we require here. And when we come to scale it, we need to make sure that we maintain those metrics over scale. So that's why I really divide this into two parts, and I'd like to talk about each of those two parts and what I say today as well. So the first thing to say is that if we're going to try to intensify the process, that's what I'm referring to here as engineering improvements. There are different ways of trying to make this improvement. We can either use process engineering, so altering conditions, or maybe the reactor, or techniques like in situ product removal, or we of course can use protein engineering and techniques like enzyme engineering. And using these techniques, and it's interesting, you know, we have a mixture of techniques here, and it's normally the combination that we require. We can then start to improve enzyme stability and product concentration, and indeed reaction rate as well. Of course, we need to know also what kind of improvements do we require. And for some time now, we've been working with these economic metrics. They're a little bit similar to the economic metrics which we have for fermentation, where we deal with titer, rate, and yield, often given the acronym TRY, T-R-Y. But for biocatalysis, of course, it's also the yield is also important, and the titer or product concentration, because this is what determines the cost of the downstream process. But here also then we need to take into account this trade-off, the trade-off between specific yield or total turnover number. So in other words, the number of grams of product I make per gram of biocatalyst, and then also the productivity, how fast this reaction goes, because this productivity, I have it here in units of grams per liter per hour. Of course, I can always get that productivity to be higher in a biocatalytic process simply by adding more biocatalyst. But this may come at the expense of the specific yield or the total turnover number. So it's about trying to get this trade-off and this balance correct. And in this small article here, I actually describe a little bit about this trade-off and some of the challenges indeed of using these economic metrics. But we see these metrics being used more and more widely, and people really start to compare processes based on the economic metrics. And this is a very good way to ensure that we get adequate intensification. What is a little complicated with this is that these metrics, of course, vary depending upon the conditions that we are testing the metrics in. So if we test our enzyme in the laboratory, we maybe have one set of conditions. That could be very different, these conditions, to actually where the enzyme comes from in nature. And of course, the conditions we have maybe in an industrial reactor are different yet again. You could argue that it would be very interesting for us to have maybe standard conditions so that we could really compare the metrics of different enzyme catalyzed processes. And that's something which, together with the University of Stuttgart and Jürgen Pleiss, we are trying to think about how to do this kind of standardization, or also to have machine readable data that we can move between one lab and another, and that's described in this short article here as well. So when I think about enzyme engineering, for example, for process implementation, then the chemistry needs to me things like substrate scope and selectivity, new substrates, new reactions, and pathways. But when I think about the process needs, well, that's the rate and stability, but it's the rate and stability under the required reaction conditions that I'm actually going to use in my industrial process. So it's also about understanding what those kind of conditions are going to be. And my view about scale up is very simple, as I show here. Here's the big man and the small reactor, and here's the small man and the big reactor. So the basic concept is that we simply are going to go up in size here. And of course, when we go up in size, an obvious consequence of this is that we have localized concentrations. So one part here is at one concentration, another part here is at another concentration. And of course, that has an implication for an enzyme. Here is an example of a bubble column. It's several hundred cubic meters just being put up in a plant in the United States. Here's a man down here, just to give you an idea about scale. And you can easily imagine in a reactor like this, well, one part of an enzyme is down here, another part of an enzyme is over here. Well, of course, it's going to be, you know, the different parts of the reactor will have very different concentrations, different concentrations of oxygen, let's say, different concentrations of substrates, of products. And this will have an effect on the enzyme. It will have an effect on its kinetics, also on its stability, but maybe even on its selectivity as well, depending on the type of reaction that we're doing. So this is really important that we try to understand a little bit about that. And I think in my journey over the years, I've been very interested in how we get from the lab over here to an industrial process. So what I'm broadly terming as scale up. What I think has become very interesting to me in the last few years is how also to go the other way. So how to come from an industrial process and say, can we scale that down so we can do experiments in the lab which really mimic what is going on at a much bigger scale. And so that's become a big part of our focus at DTU. Just to give you an idea of the type of differences I'm talking about, if you imagine in natural conditions, maybe we have a low substrate concentration. In the laboratory, well, often we also have a low substrate concentration there, but the aim should be to use high substrate concentrations in the laboratory. But what's interesting when we come to industry is now we see maybe fluctuating substrate concentrations. So any tank over some hundreds of liters will have these kind of fluctuations inside, depending on how fast the reaction goes. And that's also important to say that an enzyme reaction, of course, can go at quite a speed. We can easily have 20 to 40 grams per liter per hour. And this will really create some gradients, much more than we might get with fermentation, for example. Could also imagine if I have a gas as a substrate, we have a low partial pressure. In nature, we have a low partial pressure in the laboratory, maybe fluctuating partial pressures or higher partial pressures in an industrial tank. And the same applies for pH as well. We have a constant pH in natural conditions, perhaps it's buffered in the laboratory. Perhaps we add a neutralizing acid or base when we come to industrial conditions. So these are the types of differences that we're seeing between natural conditions, laboratory conditions, and industrial conditions. So what I'd like to do now is take you through four kind of cases or case studies, which show a little bit the type of work which we're trying to do. And the first case study I'd like to talk about is what I'm going to call here the gas-liquid interface problem. And we first started to become interested in this when we carry out a reaction. This is with an oxidase, HMF oxidase, hydroxymethyl furfuryl oxidase. And we look at the stability of this enzyme. It's not carrying out a reaction. We're simply exposing it to different agitation rates. So when we operate quiescent with no agitation, that's this orange line here. And now you see the decrease in activity, which we get at higher stirrer speeds. I plotted this here, assuming we have a first order deactivation. So as the log of the ratio of the activities as a function of time. So you can see here in about 2 hours, we really, at 600 RPM, we really lost the activity of this enzyme. We have no bubbling here or anything. We're simply stirring a tank. And when we are looked into that, what we can see is that we are drawing down some air from the surface of the tank. So here you see at a low stirrer speed, and here at the higher stirrer speed, now we're drawing bubbles down from the surface into the tank. And these bubbles seem to cause some effect on the stability of the enzyme. So that was very fascinating when we started with that. And then, of course, we wondered, well, what happens when we actually have to bubble oxygen? What would happen if we really needed to use oxygen? So we have been studying that with another oxidase enzyme, NADPH oxidase. For those of you not familiar with it, there's an article here which summarizes a little bit the potential of these types of enzyme. But essentially, we take NADPH and oxygen, we make NADP plus and water with this reaction. So it's actually a very nice reaction for regeneration of NADP plus. But of course, it requires molecular oxygen. And our way to deal with that is simply to bubble oxygen into the system. And you can easily argue, well, maybe we should immobilize the enzyme so it's kept away from the interface. But we actually want to understand what is the issue behind this. And to start with, we have done some kinetic analysis, which shows some basic data of the NOx activity as a function of NADPH concentration, also the activity as a function of the NOx concentration. So I think we understand reasonably well what is going on here. And then what we wanted to do was to test, well, what happens when we put this enzyme actually at the interface here between a gas and the liquid. So here, let's take air. So of course, it's got nitrogen and oxygen. And now we put the enzyme at this interface. What is going to happen to the enzyme? And to do that, we designed together also with Andy Bomarias from Georgia Tech, who's been collaborating with us on this, a defined gas-liquid interface apparatus. So rather than having lots and lots of bubbles in the bubble column or rising here, the idea is that we go more slowly and more defined. We send one bubble at a time up the column here. We know the size of the bubble. We know how fast the bubble rises. And we can calculate, of course, the specific interfacial area from this. So we know how much area we're coming into contact. We know the protein concentration and so on. And this, therefore, proves a very, very useful apparatus for us to understand what happens when an enzyme comes into contact with a gas-liquid interface. It's kind of interesting. When you look in the literature, you find very little written about this. There's almost nothing in the enzymology textbooks about this topic. Here's some typical data for what we find. So now we're looking at different air flow rates. So this is 0.25, 0.5, 0.75 VVM. So this is the volume of gas per volume of reactor per minute. There's a standard way of measuring the gas flow rate. And now I'm plotting out the residual activity as a function of the incubation time here. So we're simply exposing the enzyme to this interface. And you can see here over 60 hours, we are losing a considerable amount of activity. The NOxes are known to be not particularly stable enzymes. But what's very interesting is that as I go up in flow rate here, we also start to see that the enzyme somehow becomes more, not less stable. Another very interesting observation is that there seems to be, if I plot this as a log, assuming it's a first order deactivation process, interestingly, the first part, or there are two parts to the plot. The first part goes relatively slowly, and then after a while, we suddenly move to a second part to the plot. We still don't have a full explanation for what is going on in these cases. You can actually do some mathematics around this to understand what's going on to the amount of protein per area. And indeed, as we increase the flow rate, I expect that this protein per area to decrease here. So it's actually kind of strange to me that we end up in the situation that it's actually more stable at the higher flow rates. It's something we continue to look into, and we are trying to test various concepts and ideas there as well. Another very interesting observation from this was also to try different gases. Clearly, when we're doing the reaction, we're going to supply air, maybe oxygen. But most interesting here was also to try nitrogen. So what would happen if we put another gas in here? And it's very interesting that the nitrogen really did damage to the enzyme. So here in just 2 hours, we lost 80% of the activity compared to operating over here for much longer periods of time. So these are also very interesting observations. We look into this. As I said, there's nothing in textbooks about this, but it's something we want to understand in order that we can know how to solve the problem. It might be that putting behind a membrane, the interface, it might be that immobilization is what will really help us on our route here. But for now, anyway, we made a kind of operating window in the style that I've done with many processes in the past. So here we have dissolved gas concentration and NOx half-life and protein concentration after bubbling as a function of the oxygen concentration. I think I should say a very interesting observation as well is that quite some of the protein, and this is the protein concentration line here, quite an amount of the protein actually sticks to the interface and is attracted by the interface. There's also, of course, a loss of specific activity in solution, but it's amazing how much protein is actually removed and then makes its way to the top of the column, either as foam, and then it may precipitate. And then we also see some precipitants at the bottom of the column as well. So these are all things that we continue to look into in order to understand what is possible. And I should say that some enzymes are much more stable than this. This is just an example of the NOx enzyme and what is possible here. So what we found so far is that enzyme is lost from the bulk liquid to the gas liquid interface. There's some precedent for that actually in the scientific literature, for example, with monoclonal antibodies, also with some model proteins. Air is actually particularly effective at removing enzyme from the bulk for whatever reason. The specific activity of residual enzyme depends also on the type of the bubbles, and we've also done experiments where we put in nitrogen and then oxygen, and then the other way around, oxygen then nitrogen. We know that the nitrogen is also particularly harmful there. And some enzyme is lost, as I mentioned just now, via foam when the bubbles reach the surface. If we had mammalian cells in here, of course, we know that when the bubble breaks on the surface, that also does a lot of damage. That's something we're also starting to look into. So we've been starting to publish what I'm going to say here is mostly our observations, but we gradually move towards building some kind of a model about what is going on and an understanding here. And hopefully in that way, we're also going to be able to come to some kind of solution here as well. So that was the first case study about gas-liquid interface. The second study is about oxygen partial pressure. And this is also a case which can arise, of course, with P450 enzymes where we need to supply oxygen. So this is also a relevant topic for the P450 scale-up. When we work in the laboratory, we have a reactor over here with these little red dots, which symbolize the oxygen bubbles. We put in oxygen, and we assume that in the laboratory that the gas is what I'm going to call here well mixed, meaning that the bubbles can contact each other, they may coalesce, they may later disperse, but that's a normal situation that we expect in a small scale reactor. When I move to a pilot scale reactor, so even here we might be at even just 100 liter scale, we will start to see some gradients in the concentration of oxygen in the gas phase, or the partial pressure as we call it. So this partial pressure is now different at the entry point here and further up here. And that's because the bubbles, when they rise, they don't have the same opportunity to have contact with each other in a larger reactor. And we know from very big scale reactors that that's really a major problem in fermentation, which needs to be calculated and taken into account. But it might be even more important where we have a really fast reaction. We really try to consume the oxygen for our enzyme. So when I look at the oxygen transfer rate here, is the constant KLA times a driving force. And this driving force is now going to depend where I am in the tank. So that's one thing to say, that the partial pressure of oxygen changes, and that may also mean that the concentration of oxygen in solution in equilibrium with that also changes. The concentration in the bulk of the solution over here, so that's this CO, this may actually also change, because in reality, in a larger scale reactor, we may not be able to mix the liquid in a way that it's completely homogeneous and the concentration is the same everywhere. So what we start to see here is that we have a complex relationship with this oxygen transfer rate. And that made us think that what we really want to understand is what happens to the enzyme at particular concentrations of oxygen. In other words, to try to find out what the Km for oxygen is, and to really understand how effectively we use oxygen in these types of reactors. And that took us to some work at MIT, which they've been doing, where they have been operating a tube-in-tube reactor. So the idea here is that we send liquid on an inside tube. So here, in our case, this would be the enzyme, the substrate, and then we supply gas from an outside tube. And the concept here is that the gas will be supplied from the outside. The inside tube here, the membrane here, is permeable only to the gas. And this means that the gas can make its way across into the liquid. It's a very tiny scale, so we know the concentration across here will be the same. And we supply the gas here from the outside such that it will be at a constant partial pressure, meaning the concentration inside here is constant as well. So this is the setup that we built. This is a constant partial pressure apparatus. We have a tube, inside tube here, which is fed with enzyme, with substrate and buffer. And then we have an outside tube. It's on this part here. And here we're feeding oxygen and nitrogen in known ratios. We need to send it through a humidifier as well, so we don't extract water from the inside part of the tube. And then we send it through the tube-in-tube reactor. This is a few meters long. And then we measure how much conversion of the substrates we have at the end here with a UV-vis system. We can adjust the pressure in here, and adjusting the pressure up to 10 bar, of course, can also alter the partial pressure of the gas on the outside tube, as also can, of course, changing the oxygen and the nitrogen here. If you want to know more about this, it's described in this little paper here, where we talked about building this apparatus and how to operate it. We validated that also with an oxidase system. So with glucose oxidase, so very simple reaction, taking glucose to glucono 1,5-lactone, spontaneously hydrolyzing to gluconic acid. So over here, we're measuring gluconic acid as a function of the residence time. Here, the activity of the enzyme as a function of enzyme concentration. I should say that we also add catalase in here as well, and that's because this reaction will produce hydrogen peroxide as a byproduct. The catalase then produces water, and we shouldn't forget that it will also produce a half mole of oxygen, which can be recirculated back again here to the oxidase. So this is all part of the stoichiometry we of course had to look at as well. Perhaps more interesting is to see, well, what happens when we operate at higher pressures or varying pressures. So here we've operated at a higher pressure so that we can have an oxygen concentration in solution of around about 7 millimolar. In equilibrium with air and ambient conditions, we're down here, we're at 0.25 millimolar, just to give you an idea how low the solubility of oxygen is in water. And interestingly, down here, you see that we're really not making use of the available enzyme activity. We're far off reaching Vmax. This is also why we, of course, need to carry out these type of experiments so we can measure a kind of KMO for the enzyme in this way. This KMO value has implications also for how efficiently we're really using the enzyme. So without going into the details, just to say that we can derive a kind of expression from the Michaelis-Menten equation for the efficiency with which we use the enzyme activity. That's the concentration of oxygen divided by the concentration of oxygen plus KMO. So you imagine if KMO is the same value as the concentration of oxygen, then this will be 1/2 or half. So we're only using 50% of the available enzyme activity. So that's also what I show on the plot over here. Of course, it's a function also of the concentration of the substrate we're trying to oxidize divided by its Km as well. But it's clear that in an industrial setting, of course, this concentration of substrate will be very high, except at the end of a reaction. So this is also quite interesting because these values of CO are relatively low. It's quite easy, of course, that the KMO can become significant in this equation. And this means that we really don't use the enzyme in a very effective way. Actually, if you look in the Brenda database, I show here reported values for KMO for different types of oxidation reaction. And what you see here, and that's quite interesting, is how many of them are either at this value. Remember, this will be 0.5 efficiency, 50% efficiency, or even higher. And of course, you can also ask the question, well, why has evolution not fixed the problem? Well, I guess the pressure was not there to really be able to do this. And it might not even be helpful inside a cell to be able to do this. But from an industrial process, of course, we would like to use the enzyme in an effective way. So trying to get a lower value of KMO is one of the solutions to this oxygen problem, as I see it. There's a very interesting paper here which describes a little bit about the evolutionary pressure or not for these kinds of systems as well. We set about trying to test that, and in a very nice collaboration with BASF and also with Nick Turner from Manchester, we tried to convert HMF to DFF using galactose oxidase. This is an enzyme originally from Francis Arnold's lab. It's been modified many, many times, but this is quite an interesting reaction to carry out. But from our perspective, we're also interested in trying to understand a little bit about this how effectively we use oxygen here. So what we tried to do was to take various variants and to have a look at the values of not only the Km for the substrate and also the Kcat of the reaction, but also the KMO of the reaction. So we measure this in the tube or the constant partial pressure device. What is interesting here, of course, you can screen in such a way that you put some pressure and then you, of course, get some improvements for the Km for the substrate. Value goes down, Kcat goes up, that's fine. But we also see that the Km for oxygen goes up. You get what you screen for, you don't get what you don't screen for. So that's also the situation a little bit here. That now we realize, well, we need to put some kind of pressure on the system in order to make sure that we really get some improvements here in the KMO. Otherwise, we end up that we really don't use the enzyme effectively. And this is also a challenge, of course, for oxygen supply. So we then had the idea to operate in a glove box. And the idea here is to really operate almost in a vacuum type system. And then we indeed were able to lower the KMO as well. What is interesting here is that this value is, of course, about the same as our starting value. And it raises a question about whether for such a small molecule, you can actually reduce the KMO still further. That's still an open question. But if you want to read more about it, it's in this nice publication here where we describe some of the techniques which we have used and the importance of the KMO. And we also, in that paper, have talked about the two aspects of trying to improve an enzyme for an oxidation reaction. So one part of it here is what I call biocatalyst-driven process design. And another part here is about process-driven biocatalyst selection. So we need both these parts. And in stages, then we take into account the rate, yield, productivity targets, oxygen supply, in situ product removal, because the product turns out to be inhibitory here, activity, the KMO, and then ultimately the conversion as well. So we end up with an enzyme with a total turnover number of 10 to the 6 and operate about 150 grams per liter of HMF in here. So we're on our way towards making an industrial process from this. So the concept here is really that we use some kinetic analysis, which comes in this case from this constant partial pressure device. We use that to improve the catalyst. And then having improved the catalyst, we use that to really drive the process here as well. And I described that in this kind of concept in a number of papers here as well. So the third example I'd like to come to concerns a little bit bottleneck identification. I think we're all familiar with the situation where we have a reaction and we discover there's some kind of bottleneck or problem in here, and it's very good to know what that problem is as soon as possible in order that we can put the solution there. And one route towards that is to try to do some kind of cost estimates of process. And this is a P450 reaction expressed in the E. coli, which we've been looking at, or we looked at in the past. And here, one of the things that we identified rather quickly was, well, it's not just a matter of the substrate and product related parameters, even these process parameters I talk about here, but also many things to do with the biocatalyst. For example, when we are growing the cells, what cell density do we achieve? What kind of enzyme expression levels do we achieve? Because, of course, probably with this type of enzyme, we're talking about operating inside a cell or maybe as a microsome. So we need also to think about that. And then I put some other things like coupling efficiency as well down here. And that's quite aside from the questions about the stability. If we operate in a cell, it's a question of cell stability, but also the total turnover number, maybe for the monooxygenase, the reductase, cofactor. So there are quite some things, of course, to think about. So we move up a whole order of magnitude, I think, in terms of complexity with some of these types of systems. A quite interesting analysis we did, which we published in this paper here, was where we look at the expression levels inside a cell and what kind of specific activity that is able to give us. And ultimately then, okay, what kind of cell concentration we can achieve, so how many gram cell dry weight per liter, what implications that has for oxygen supply, so there might be some limit to this set by the oxygen supply, and use that data to guide us a little bit about based on the stability of the cell, what kind of product concentration we will get for a given space-time yield. And ultimately, you can use that information to give you an idea for a resting cell process, so a metabolically active system, but not one which is growing, to show here what happens to both the specific activity, but also the product concentration as well. And this gives us an idea, okay, the changes or the implications of what happens even back here in the expression level, on what the consequences of that are for a process, and putting that process in place. We actually put this into SuperPro Designer. This is a very simple model of what goes on. We have a fermentation, we wash the cells afterwards, and then we go through a transformation step. So we've decoupled here growth from conversion, which is a strategy we are using in many types of whole cell reactions. So the concept here was to apply a number of assumptions to this, and we end up with a cost around about $1,000 per kilo. If you make improvements to the enzyme expression and stability, that can bring you down a whole order of magnitude. And we're still not, of course, at the values that we require, but it was quite interesting. If you do a sensitivity analysis on this to understand the changes in the expression level, the effect which that can have on the production cost, likewise the stability as well. So here shown as a total turnover number, or but now we put it in mass basis, so grams of substrate per gram of enzyme. Again, you see here the way in which the production cost can really fall here. So this is very interesting to understand this sensitivity, because it also says how important it is that we look at these questions like expression. Maybe not the most exciting topic to look at, but super important in order to bring down the cost for this type of process. Interestingly, these P450 reactions, of course, could be operated with decoupled growth and conversion, as I show in the bottom flow sheet here, but they can also be run, of course, in the same reactor as well. So now I have the fermentation and the transformation together. So that also made us at the time look into different P450 processes, what happens with growing cells, what happens with resting cells. And here I plot out a space-time yield as a function of product concentration. We are still not at the kind of required values. We also don't see major differences here, I think, between the growing cells and the resting cells. So it's this old story we had with P450s for a long time now. In this case, we have a more stable enzyme, but it doesn't go so fast. In other cases, we have something which is going fast, but it's not so stable. So we're still ending up with the same kind of total turnover as well. Some more details about this are given in this paper here. And what I can say from this is that, of course, we require much more research on P450. So the relationship of oxygen concentration and expression, the oxygen demand for both growing cells, for resting cells. Microsomes are another question, of course, and another way that we might consider operating this system. Process methods for working with compounds which have high volatility, low water solubility, high toxicity, and maybe if we really operate in the environment of a cell, which may give extra stability to the enzyme, still we have to deal with poor transport in and out of the cell, depending on the type of substrate that we have as well. Fourth and last case study I'd like to talk about is inhibitory and toxic co-substrate feeding. So this is a situation we see with many types of reactions where we have one of the substrates which is inhibitory or toxic, and how to really to be able to deal with that situation. So here I just give you an example of work we've started to do on unspecific peroxygenases. So here we look at cyclohexane oxidation using peroxygenase at a 10-liter scale. So this is our reactor over here. We, of course, did a lot of preliminary work at a small scale before we start to scale this up. But it's a very nice collaboration with Technical University of Delft with Frank Holman. And here we take cyclohexanone plus the hydrogen peroxide, and we can convert this to cyclohexanol or cyclohexanone. And the key thing here is that we need to feed the hydrogen peroxide. And of course, we try to keep an eye on that and to understand what's required. So here we are looked at the kind of feeding challenges here of hydrogen peroxide. Now we can keep the concentration relatively low in the first part, but after a couple of hours, it starts to rise. And of course, we're now in a cycle that we really do damage. The higher the hydrogen peroxide concentration, the faster we lose activity. So the questions from this are kind of how to feed hydrogen peroxide, what concentration should we use, where to feed the hydrogen peroxide in the tank, especially you can have a bigger tank where we have concentration gradients, back to the discussion we had at the beginning of the lecture as well. So just let me come to a summary here. What we're trying to do at DTU and my lab is to develop new tools so that we understand a little bit what these industrial conditions, what kind of effects they have on enzymes. And it's not that we come to solutions yet, it's still more fundamental to understand what is really going on. It's a topic which is hardly studied in conventional enzymology, but I think of great relevance if we really want to implement these processes. We're using this kind of scale down approach. We have several pieces of special apparatus, which I've given you a couple of examples this morning. We have limited models available, but of course our aim is actually to build mathematical models of this so that we can really make predictions about what will happen. And this could be really great because then we can link what happens when we have an intensified process, what's going to happen when we really come to scale then as well. And then we also work on integrating bottleneck analysis and understanding where the limitations are in these processes as well. In the context of the research hub, I think it's important just to outline a little bit some of the things which I think are very important to look at with P450s and UPOs. This bottleneck identification linked with improvement methods, process design, and so on. But for P450s, of course, we are interested in studying kinetics and stability in the constant partial pressure apparatus, also in the new gas-liquid interface apparatus as well. Another question which we would like to address is what format of biocatalyst we should be using. Should we be using a growing cell, resting cell, or a microsome? And when should we use those? I think when we're designing a process, it's one of the very first questions we always have. Well, what will be the format of the enzyme? So should we collect the data under the right formats, and how to know what that format should be? So I think this is also an important scientific question to answer in the concept of process design. And for UPOs, of course, this hydrogen peroxide, how to deal with this is also a very important part of what we're interested in. And I can say for P450s, maybe we can think about oxygen surrogates as being another interesting way to deal with this, just as for UPOs, there can also be other ways as well. So that's what we're also interested in trying to examine. So I'd like to finish just by thanking my team, the various excellence collaborators that we have, and of course also the funding, and then just say that, what we describe here is the scale-up part of this hub activity, but of course this will be integrated together with a lot of the other aspects here. Last week there was a webinar about the issues. Some of the issues are techno-economic issues as well. I think this also relates and links into some of those business issues as well, just as it does to the type of extra stability which Liz was describing in her very nice presentation at the beginning of this series of webinars as well. So I'll finish there. Thank you all very much, and happy to take questions.
Thanks very much, John. Let's open the session up to questions now from anyone in the audience. Please feel free to turn your microphones on.